Hi Math Crew. I've had some requests for some assistance on the style of problem where we have a sequence of figures and we're counting some feature and trying to spot a pattern. So in this one, we want to count the number of shaded tiles in each figure. So case number 1, I think, has 4 tiles that are shaded. Case number 2 has 3, 6, 7, 8 tiles that are shaded. Case number 3 has 4, 8, 9, 10, 11, 12 tiles that are shaded. And then case number 4, let's see, that's 5, 10, 13, 16 tiles that are shaded. So the first thing we want to do is make sure that we know how to count whatever is being counted. And I know that sounds a little bit silly, but it's easy for us to cruise through the problem and assume we know what we're talking about rather than being really careful up front. So I just want us to be really careful up front. Put the brakes on, make sure that we're counting correctly. One of our jobs with problems like these is to try to spot a pattern so that we could find the number of tiles needed in case number 432, for example. I don't want to draw all of the figures out all the way to case number 432, so I'm hoping we can spot a pattern within the information that we have. I like to organize my information in a table like this where I put the case number in the left-hand column and the number of tiles or whatever we're counting in the right-hand column. And then I take a look and notice that the gaps between the outputs, or the number of tiles in each case, are the same every time. It looks like we increase 4 tiles every time we move to a new case number. And that is going to be really helpful for us. When we add 4 onto something repeatedly, there's actually a multiplication by 4 that's going on behind the scenes somehow. So if I try multiplication by 4 right now against a case number, let's see what we get. If I take the case number and multiply by 4 each time, well, 1 times 4 would be 4, and that's the number of tiles in case number 1. If I do case number 2, I would take 2 times 4, and that would give me 8 tiles, just like we have in case number 2. And then I can keep trying. 3 times 4 for case number 3 gives me the 12 tiles in case number 3. 4 times 4 gives me 16 tiles, and that's the number of tiles in case number 4. So it seems like if I take the case number and multiply it by 4, I will get the number of tiles that I need. And some of you might be kind of equation or formula oriented, and so we could write this in a formula format as, let's use C for the case number. We would multiply 4 times C, and that will give us the number of tiles, so capital T for tiles. Something like that if you want an equation. But I also like this sentence about what to do to our case number to get to the number of tiles. And then we can extend a little bit. We can say, okay, if I have case number 111, if I wanted to know about that, it has, well, we would take 4 times 111 to give us 444 tiles. So that's how this one would work. They're not all as straightforward as a single multiplication, so let's extend this a little bit with a different example. Here's a different set of figures. The little squares are intended to all be the same size. If I start kind of the same way as I did last time, organizing things in a table, figures 1 through 4. Figure 1 has 1 square that it's made up of. Figure 2 is made up of 4 squares. Figure 3 is made up of 7 squares. And figure 4, if I count all of those, that is made up of 10 squares. So I get my information organized, and then I look to see how are these figures changing the number of squares each time. To go from 1 to 4, I increase by 3 squares. 4 to 7 is also an increase of 3. 7 to 10 is also an increase of 3. And we had something similar happen in the last example where I said, oh, if we have a bunch of repeated additions, there's really a multiplication lurking behind the scenes. I think we will have a lurking multiplication here, but something else happens as well. So if I came along and said, let's take the case number and multiply by 3 for all of these repeated multiplications, let's see if that works for us. So if I do case number 1 and multiply it by 3, I get 3. And I wanted to get 1. And this is not looking good. Let's try case number 2. Case number 2 would be 2 by 3. And that gives us 6 instead of 4. Case number 3 times 3 gives us 9 instead of 7. And case number 4 times 3 gives us 12 instead of 10. So none of those is working right now, and that seems like it's not good news. But there's a little twist we can do, a little adjustment in each case that will fix each of these for us. And so I recommend that you take a look at 3 versus 1 in case number 1, 6 versus 4 in case number 2, 9 versus 7 in case number 3, and 12 versus 10 in case number 4. And I'm hoping that you'll notice that there's a gap, a difference of 2 squares in each case. So if I came along each time, I didn't leave myself enough room here. If I took the case number times 3 and then subtracted 2, I would get the number of squares that I need. Let's try it each time. 6 minus 2 is equal to 4. 9 minus 2 is equal to 7. 12 minus 2 is equal to 10. This takes 2 steps to get to our pattern. And so if we wanted to write a rule about this, we would take the case number. Oh, it should have been the figure number. Case number was last time. Take the figure number and multiply by 3. So we do that first and then subtract 2. To get the number of squares. If you wanted an equation for this, let's use f for figure number. We would multiply it by 3 and subtract 2, and that will give us the number of squares. Oh, I don't like s for a variable. Mine start to look like 5s. If we were in need of figuring out how many squares there are in figure number 300, let's say, we would do 3 times 300 and subtract 2. This will be 900 minus 2, so 898 squares. So the repeated additions give us a hint about multiplication being useful in the pattern. And then sometimes there's this extra fix that needs to happen as well, this extra little fudge factor. And if you don't like how that's kind of mysterious, there is another way to get at that. And I was hoping for a different color of pen, fishing around for a red one. All right. In the table, if we were to go backward up the table, 4, 3, 2, 1, 0, and then go backward up the table on the right-hand column with the number of squares, instead of adding 3, we would subtract 3. 10 minus 3 is 7, minus 3 is 4, minus 3 is 1. 1 minus 3 is negative 2, or a subtraction of 2. And that subtract 2 is exactly the same as the subtract 2 extra component to this pattern. So if you can work your way backward up the table to a place where we are at the 0th figure or 0th case, then we can pull off its partner as our extra component. All right, I hope this helps. If you have questions, please reach out.